I can hear you.
Perfect. Hello, everybody. Welcome to our webinar today. The topic for discussion is an introduction to the Python package Scikit-Learn with your professor, Dr. Michael Perch. I just wanted to go over a few logistics for those of you that are joining us for the first time. My name is Avi. I'm the product manager here at Datum. Should you have any questions, I'll be behind the scenes. Feel free to message me. So first off, please make sure that during the class you are on mute. Michael does love participation though, so if you would like to participate, we have two options. There's a hand raising feature on your screen as well as a chat feature. We can answer any questions or take care of any logistical or technical issues as well. I'm also behind the scenes. My name is Avi again. You feel free to email me. My email is avi@datum.io. Also, we love receiving your feedback, or if you'd like us to teach a class at your company or further any discussions, we love hearing what you have to say. So please feel free to go to datum.io/feedback and fill out a quick questionnaire there. Always open for discussion. Secondly, if you would like access to this content or any of our future webinar classes, we are open sourcing our content for a limited time. So we are creating a waitlist right now. I know many of you are joining us from some of our previous webinars, and please bear with us as we fix some of the bugs and make sure that we are 100% ready for production. If you'd like to join our waiting list to get access to the content, the website is datum.io/access, and there you'll fill out a quick questionnaire with your name and GitHub username. And as soon as we launch, you will have access to our content on there. And finally, we have many webinars, classes, courses planned with Dr. Perch as well as Dr. John Foster. If you are interested in continuing your education with us, please visit datum.io/events. We have quite a few events planned for the rest of the year. So really quickly, I'd like to show you a few of these before I hand it off. Share screen, Chrome, share. Perfect. So the first page here is our feedback form. You can just quickly fill out your email. And then at the bottom, you'll notice that if you would like us to come teach a class at your company or anything like that, feel free to fill in this spot here and we're happy for any discussions. This next page is access to our content. So it's just datum.io/access, and you'll fill out this form and you will be put on our wait list. And as soon as that launches, you will have access. What does that platform look like? This is our Jupyter Classroom, which we are currently building out and developing. So as you can see, we have a few classes here on the fundamental side: energy machine learning, energy data science in Python, subsurface machine learning, as well as some other courses that we're building right now. Pandas for Excel users, automating the boring stuff, spatial continuity. So you will have access to this content. And finally, this is our events page on Eventbrite. So if you go to datum.io/events, you will find a series of our upcoming events, micro courses, virtual workshops, and anything that you may be interested in. We're always ears open. So if there are topics or anything that you'd like us to cover, we are always here for input. Perfect. Now I'd like to hand off the baton to our CEO, Kunal Riker, for a quick couple words before Michael starts. Kunal, the floor is yours.
Can you guys hear me okay?
We can hear you.
Perfect. So let me, hi everyone. My name is Kunal Riker and I'm the CEO here at Datum. Appreciate you all spending the next hour with us as we start to explore the Python package Scikit-Learn. Thought I would just give a minute, giving you a little bit of background on who Datum is for those of you who are new to our company and our team. Datum is an energy-focused data science education and training company. We do the hard work of translating the best of what data science and code has to offer into something useful for us as energy professionals. Our MO is to really build interdisciplinary training programs that marry geoscience, petroleum engineering, and data science together and to teach those programs to professionals like yourselves who want to learn how to implement these skills. As an example, from a few of the partners we've worked with to date, we've helped save over 10,000 hours with some of the workflows and tools that we teach, some of which using the package Scikit-Learn that we're going to walk through today. And so overall, we kind of think about education via a three-pronged approach. Workshops where we really introduce data science concepts, enterprise programs where we help you guys build workflows using your data. And third, as Avi alluded to and quickly previewed, is our self-paced learning management system that you can kind of go on your own self-paced learning journey and learn all the skills and tools you need for success. And so a little bit about our team. If I had to summarize it in one word, it'd probably be multidisciplinary would be the word I'd use. The Datum team is comprised of geoscience, petroleum engineering, software engineering, and finance professionals. So whether you're interested in learning something engineering specific, geo-specific, finance specific, or even HSE specific, our team can help you apply data analytics and data science to whatever workflows you're interested in building. All you really have to do is just ask. And so with that quick introduction, I'm sure you're all itching to learn something about Scikit-Learn. I'll hand it off to your lecturer for this afternoon, the one and only Dr. Michael Birch.
No, thank you very much for the introduction. I do appreciate an Avi too. Everyone can hear me okay? Everyone can see my screen?
Yep.
Yes, Michael, we can see it.
All right. So just a roadmap. This is what we're going to do this afternoon, and we're going to do this in 1 hour. So this is a little bit ambitious. Just a very quick introduction to myself, really just so you know where I'm coming from and how to contact me and so forth. And we will also then talk about motivation, one slide, talk about machine learning concepts, terminology. That may be the longest part of this discussion because we can't show models, show Scikit-Learn, do things in Scikit-Learn if we don't understand some basics. Now, I warn you, this is a race to model kind of 1 hour, so please do not expect us to cover all of the salient details, but we just want to give people a bit of a sampler, a buffet that we can try out today together and gain some experience. I want this to be interactive. I will have the chat window open, so anyone, if they have a comment, question, shoot it into the chat window, of course, or I'm cool if you want to unmute yourself and ask a question at any point. So then we're going to go ahead and cover the basics of Scikit-Learn and how we build machines in Scikit-Learn, which is wonderful. It's an incredible, flexible package. Then we'll cover a simple machine. Suspense should be killing you now. What is that simple machine? Mapping in predictor feature space with another machine, because I think a lot of geoscientists who might be on the call will appreciate something that's an extension of mapping. They map. Segmentation in predictor feature space, a little bit more advanced methodology, and then we'll get into projection into higher dimensional space. This will get kind of cool. So let's go ahead. We may not have as much time for this last one. We may be a little bit tight there, but we'll cover some. You'll get some experience here together. Introduction. If you've never been in one of my classes and at any point you're going to want to say something to me and be a little uncomfortable about how you address me, Perch is pronounced just like this, Perch. My family's been in Canada for 100 years. We lost our ability to pronounce our own name. I've met Ukrainians who tell me we say it wrong, but Perch is fine with me. I'm from industry. I did start as a professor in 2017, but I do have a lot of practical experience in spatial data analytics, stochastic modeling, decision-making in the presence of uncertainty, and all different types of modeling methodologies. I'm very flexible. I am happy to adjust the rate at which we're going if there's lots of questions. This is always learning directed or guided. It's not a schedule guided. It's all about let's gain some good experience, some knowledge from today. And I'm available. Go ahead, drop me a line sometime. People do. I'm happy to discuss. I'm an engineer and a geoscientist. I do speak both. I'm bilingual, and I frequently teach and consult in our industry. I work with a lot of working professionals, and so I know something about the practice. I'm not a professor who's isolated by any means. And I also have a lot that I share on social media. Twitter, GitHub, my YouTube channel, and so forth. Check it out because I'm very much into supporting working professionals and students. So I do share a lot of content. Okay, I promise for the remainder of the hour, no more braggy type of slides. That's it. Okay, I won't do any of that. From the person who just said hello in the chat one, hey, howdy to you too. Thank you very much. The goal of what we're doing during this one day, some concepts, not all of them, we can't cover it all. And experiential learning, you can't put fingers the keys in an hour. We can't set that up. Usually we do. When we have people in a regular class, you'll be set up on our cloud and you'll be able to run all of our workflows. But we're going to just basically plow forward, race to machine learning in an hour. That's really our goal here. Don't expect all of the depth that we need to cover. We'll show some things, right? Data analytics and machine learning overview. Let's talk about that first. If you want to understand what machine learning is, you could be like many people in the world and Google search it. And one of the top responses will be Wikipedia. It always is. And you could go ahead and read that entry in Wikipedia and you'd find something like this. Is the study of algorithms and mathematical models. It's a toolkit. It's not just one model. The computer systems used to progressively improve their performance. They're learning, a toolkit of learning methods. Machine learning algorithms build a mathematical model of sample data known as training data. Toolkit, learning with training data. In order to make predictions or decisions without being explicitly programmed to perform that task. General, a method that can be generalized to a wide range of different problems. Okay, now the problem is many times when people read this definition, that was great, but they stop there. They don't get to near the end of the article where you'll get a quote like this, where it is infeasible to develop an algorithm of specific instructions for performing the task. As an engineer or a geoscientist or any other type of scientist, what I'm saying is it's not a panacea solution. If you know the fundamental physics and science behind the problem, it's best to use those approaches. We'll use data-driven approaches to assist when speed, efficiency, or when we don't understand the physics well enough. There's a variety of ways we'll use it, but we'll never use it as a crutch to avoid the engineering and the science. What is a feature or a variable? We'll be talking about that a lot in the next hour. Any property measured, observed. Now, what I would say is, modern speak in machine learning, we call it features. So we'll call them features here. Many people called them variables before. This thin section from our good friends at the BEG of a carbonaceous rock with the blue as the porosity should remind us that none of our data is given to us as a just directly measured with no pre-processing. When we work with this sample, I hope you can agree that even porosity, we would have to be thoughtful about what do we mean by porosity? Do we mean porosity inside of these grains, or do we mean effective porosity that's connected and flows? So I just want to emphasize this idea that there's always some type of domain expertise and processing. The data preparation is still 80 to 90% of our time, even when we're doing machine learning. Every time I say machine learning, I want this equation to appear in your head. This is all it is. We have a model, F. It's going to take a set of predictor features, the model inputs. Back in the good old days, we called those the independent variables for our model when we built data-driven models, statistical models. It goes in, the F function will take those, translate it to a response feature. The response feature is the model output. And back in the good old days, we called those the dependent variable or variables. Now, machine learning is all about estimating that model F for two purposes. The first purpose would be inference. The second would be prediction. Today, because we're just racing to build models, we're just going to focus on prediction. The prediction is really about getting the best estimate of that function, the one that best approximates the natural setting to give you the very best estimates of the response. Prediction's all about getting the best accuracy. Now, we want to make sure that we do that. Now, recall, in order to do that, we have to learn a lot about the population or the sample. We have to understand about the underlying system, and we have to be able to move beyond that to make the next prediction at the next possible sample. And so there's all kinds of issues that can creep in here, but we won't get into them, such as stationarity and invariance under different feature combinations and so forth. But an example of a prediction exercise would be if I give you a coin and I tell you that this coin is fair, I ask you, what is the probability of you getting 3 heads and 7 tails out of 10 tosses? That would be a very simple prediction. Now, that could be extended to exploration in the subsurface or any more complicated problem, of course. When we build those F models, that approximation of the natural setting, we have a choice between parametric and non-parametric approaches. A parametric approach, you make an assumption about the functional form of the natural setting. You gain from the simplicity of that, and now you have just a few parameters. It's much easier to estimate with sparse data. Here's an example right here of a linear model. We've got the coefficients, the model parameters, B0, 1, 2 through M features, and we have features 1 through M that we're working with. And the result is we'll get a model like this, linear. Now, of course, the problem is that your F hat, your estimation of the natural setting, might be completely wrong with a parametric model. In this case, you can see this phenomenon is cyclic and is not linear. So this is probably not suitable. Now, working with non-parametric models, they have no prior assumption about the functional form or shape, so they're more flexible. In fact, when people think about machine learning, they often think non-parametric because it has the flexibility to learn the shape from the data, from itself. So it becomes much more flexible, less risk that the F hat is a poor fit for the natural setting, the actual function. Typically, you need a lot more data for an accurate estimate of F. So here's an example right here from a decision tree. We will cover that. That's the segmenting machine learning methodology. But you'll see an example right here where it's flexible. It learned that cyclic behavior from the data. Now, one thing I want you to remember, every time you hear somebody say non-parametric modeling, I want you to realize that it in fact is parameter rich. That in fact, whereas it doesn't have that simple form with a few parameters, it actually required a lot of parameters in order to specify this form, and you had to train all of those parameters. Now, I mentioned a couple of comments about training. On one slide, I'm going to explain the entire workflow for machine learning. What we're going to do is we're going to take the initial data that's available to us. The predictor feature is Z, which is depth, and permeability. So there's some type of depth trend here we're trying to figure out. There's a datum here, I'm sure. And we'll go ahead and we'll divide the data up into testing, which are the circles, and training. The testing data, we're going to take that and throw that away. You don't get to peek. You don't get to look at it. You're not allowed. You're going to use just the training data to build the model. Then what you're going to do is you're going to take and you're going to build a model with that training data, and you'll train the model parameters. And by doing that, you'll change, in this case, a linear model such that you get the best fit with the training data. Then you're going to increase the complexity of the model and retrain, increase the complexity, train again, until you have a very complicated model. The way I demonstrated this is I just simply showed polynomial modeling, right? Polynomial regression, where you have first order, second order, third order, sorry, fifth order, seventh order, and you can see the varying degree of flexibility to the data. Then what you do is you take that best fit model for each level of complexity and you bring back that testing data. You remember that data we threw away? You're going to bring that back in again, and you'll take it and you'll measure the error or the goodness of fit with regard to the testing data. You'll do that for each level of complexity, and you'll pick the model complexity that best fit the withheld data. That is called hyperparameter tuning. Now, I've said model parameter and hyperparameter, so I better define them now. Let's go ahead and define model parameters. what you do with a model parameter is it's going to be like a coefficient in a polynomial expression, the B3, the B2, the B1, and the C, the constant, or B naught. You can change those values, and I hope you guys can all appreciate it would cause the line or the polynomial to move around, to switch its shape and change. But by changing those, we can get the minimum amount of error. And we're not going to talk about norms or how we measure that today, but you go ahead and get the best fit line effectively. Those are model parameters. They control the fit to the data. Okay, now a hyperparameter, this is a totally different thing. A hyperparameter controls the complexity or flexibility of the model. The choice of a first order, second order, third order, fifth, or seventh order, as I showed before, that's the hyperparameter in this case. When we tune that, we're picking the right level of complexity such that we get the best model. And we're doing that. If you look at it, what's very interesting, let me ask by chat window. If I was to go ahead and just pick the very best model as far as fit to the training data, as far as minimizing the error with training data, which model would I select? Anyone? Would I pick the first order, third order, fifth order, seventh order? Which one gives me the very best fit at the training data? Remember, the training data are the X's. All right, thank you very much for all the responses. I see a bunch of responses here and I do appreciate them. If you look at it, look at the training data. With a seventh order model, I can perfectly fit the training data. You see that? No error. But Johannes, you're totally correct. And Chris, you're totally correct. Because at that point, you're overfit. How do we know we're overfit? We have low error, high degree of accuracy with the training data, but we have really no confidence in our predictions away from the training data. Look at how inaccurate we are at the testing data locations. Hyperparameter tuning is all about getting the right level of complex so that we can avoid overfit. Hesham, you're totally right. Part of this is all driven by noise in the data. In fact, it's very interesting. I showed a demonstration recently. If you have very clean, not very noisy data at all, you have less risk of being overfit. So it definitely is a trade-off. Okay, good comments, guys. Hey, and I do appreciate all the interactivity in the chat window. Feel free to jump in, even unmute yourself. It's really good to have the discussion. Now, there's one more concept we have to cover, and I have to admit, we're not going to do much with this today. I'll make comments. In the full course, this would be a critical part, and I really don't want to cover machine learning and not cover this. When we're talking about the performance of our machine, what we really want to know is the expected test mean squared error. In other words, we want to know how our machine will perform at withheld data locations. Now, what we really want to know is how it will perform when we use the model in real world use. And so this effort of using withheld data is really a dress rehearsal, and it's an attempt to mimic that. Okay, so now if you take this concept of statistical expectation and the square difference between the true testing values withheld in the response versus the predictions from your model, if you expand that, and in the book, James and all, they do the derivation. It is very interesting. You get 3 additive components. Variances are additive. Isn't that interesting? And it turns out if you look at those additive components, what you'll see is that you have model variance, model bias, and irreducible error. Now, this is really cool. We can now understand the components of error. These are our enemies that we have to fight when it comes to making a good machine. The model variance is error due to sensitivity to the data set. What's interesting is that a more complicated machine will be more sensitive to the data. Do you remember that 7th order polynomial? If you changed a couple of data values, it would swing around like a whip, okay? But as you have a simpler model, model variance goes down. Now, model bias is error due to the fact that you have an approximative model. It's not flexible enough for the natural setting. What we'll see is that a linear regression model is very inflexible, has a lot of model bias, but a higher order polynomial model, it gets more flexible. It has lower model bias. Then we have irreducible error. If you could replace me with Andrew Ning, like one of the world's experts in machine learning, they could not take care of your irreducible error. It's a function of the data, limitations of the data. You just don't have enough samples. You don't have all the combinations of the features you need. Maybe you missed part of the data set. You're not seeing everything. Irreducible error is driven by limitations of data. So it doesn't matter about model complexity. It's constant. If you sum all of them together, you'll find out that the best model to work with is often not the most complicated. Usually you have an optimum model which has kind of a moderate degree of complexity. Okay, the 3 components, I will test you on that later, so please try to remember that. Okay, and so let me make a comment. People have been commenting about this whole issue around model overfit, so let's just make this clear. If you look at that performance with testing, and you'll notice it usually has this kind of a sweet spot right here, a minimization. If you look at that, what you'll observe is that in general, training error will continually go down. A more flexible model will get a better and better fit. The testing error will go back up. When we get into the region where the error in testing, the attempt at real world use of the model is getting worse in accuracy, its error is going up, and the training is going down, we're clearly in the realm of overfit. We're fooling ourselves into believing we know more than we actually do. All right, very cool. So there was a question about, can we reduce irreducible error? That actually sounds like kind of a cool movie title or something. It turns out that since it is based on the data, the only way we would improve that is by collecting more data. Yeah, or if we did something to improve the data, like there was processing, debiasing, some type of weighting or something we could do to improve our image from the data. Yes. Okay, good. And thank you very much. I do appreciate it. Okay. Let's go ahead and just mention what Scikit-Learn is. I'll just introduce it. Scikit-Learn, it's a wonderful library of inferential and predictive machine learning methodologies. It has so many of them. Go to the website, look at the docs, great documentation, and it explains all of them. It's really, really useful. So Scikit-Learn is wonderful. The thing I like about it too, though, is it's not just the algorithms. It includes a lot of the support for a machine learning workflow, including simple things like train, test, data split. Not so simple if you try to do that in a good manner, but it does do it randomly. And model cross-validation, methodologies like k-fold cross-validation and so forth. Lots of great methodologies to support your entire workflow construction. It's also it's very well documented, robust code, uniform format. In other words, when you build a workflow, it's very much plug and play. You're able to go ahead and just put a new machine in, try it out. So great for experiential learning. Now, Hisham, I do appreciate your comment on efficiency, computational load around the methodologies. While I would say the methodologies are well documented, very great for, great for learning and so forth, I am not commenting specifically on HPC use in very large applications for production and so forth. I'm talking about it as an educator. So I hope I can differentiate that for you. Okay, thank you very much for the comments. I do appreciate those. And thank you very much for the comment about this being a happy day. I have to admit, this is a happy day for me too. A day where I'm teaching and educating and helping others is a great day for me. Okay, so this is why we're motivated. Now, every time we go ahead and we do use Scikit-Learn, the common workflow steps will be there. We're going to go ahead and instantiate. Now, instantiate is a programming term. It means if you're working with a class or an object, you make it. You actually create it, and then you start to work with it. So instantiating, you make the model object. And during that process, you go ahead and you set the hyperparameters. So that'll all happen in the first step. Yeah, Sue, in this discussion today, we're going to consider just a basic introduction to machine learning. As part of our data science education with Dr. Foster, we get into more HPC, working with big data sets, and what are the fast, efficient methodologies for getting the job done in that case. That's not what we're covering today. It's really a basic introduction to machine learning. Thanks for the question. I appreciate it. So, the second step, now that we've made our machine and we've set the hyperparameters, we're going to go ahead and fit it. This is the training You're going to train the model parameters to the training data. Then when we're done with that, we can go ahead and make predictions. Now, we can make predictions with the trained model. You'd hope that you're doing cross-validation, you're testing the model performance, you're going to tune the hyperparameters, the degree of complexity of the model. For this short webinar, we will not do robust tuning of hyperparameters. Instead, we will play with hyperparameters. I'll take some votes and we'll go ahead together and change some hyperparameters and see what we get, okay? It's more just to get some learning. If we had time, we'd do more of that. We will not have hands-on. I will have a demo sessions for each one of the methodologies. We will show the machines and I'll take input as far as setting them, but we don't have the time to set up and get everybody working on our cloud as we do with our regular courses, not during a webinar. Okay, let's introduce a very simple machine. I'm a little embarrassed, but at the same time, I'll tell you what, for linear regression, I challenge my graduate students. Every time I teach my machine learning course, I have 70 students in that course right now, and nobody can ever disprove the idea that linear regression is machine learning. To me, it meets all of the criteria. So let's go ahead. We get a simple porosity versus density relationship right here with some scatter. And we can go ahead and we'll put a model. Now, this is linear regression. There's nothing intimidating about linear regression. Why do I bring up linear regression? And to be honest, I'm not even going to jump into the code for this one. I'm just going to go ahead and go to the next one, k-nearest neighbors and mapping. But I'll tell you what, why do I bring it up? Because everybody thinks it's simple. But if you start to look at the details, you're going to find out that there's a lot of details behind it. And they're instructive details. The first one being, you've got a parametric model with coefficients, the model parameters, of course. And you're going to have to come up with the very best parameters such that you minimize the error with the training data. What we do is we do a minimization of the squared error at all of the training data. And in this is a case with the L2 norm where we actually have an analytical expression for the parameters directly from this minimization. Often does not happen in machine learning. With many machine learning methods, we have to do some type of a search, an optimization, often stochastic gradient type of approaches, and we're not going to cover that today, but this is one of those topics we'd want to get into. This illustrates this idea of minimization with an analytical form, which is very useful. The other thing is that what's really funny, has anybody really dug into the assumptions behind linear regression? It is really surprising. For instance, error-free. What's interesting is that whereas we are accepting in the model error in the prediction, in other words, the response feature, the Y, we assume there's no error in the X's, the inputs, the predictor features, only the response. And that's important because we often do have error in the predictor features too. We also assume constant variance. Now, anyone who knows me knows that I have a goal personally to use the term homoscedasticity in every single day. It just makes me happy. It's like getting my vegetables, right? And so we are assuming homoscedasticity in the case of linear regression, that the error magnitude is the same, not systematically varying across the predictor features. So this is very important too. Okay, so what I'm trying to illustrate here is that there's a lot of assumptions built into linear regression. Don't be shy. Don't be surprised that when we go into other machines that there's going to be assumptions. We need to understand what's going on under the hood. Okay, so here's an example of linear regression. As I mentioned, we have the code. We're going to jump in the code right away, but I'm not going to jump in the code just for linear regression. It just doesn't seem worth it. Let's introduce one more method, and then we'll jump in the code and show both at the same time. Linear regression, it's a planar fit. I hope you can look there. As a geoscientist, we'll look there and be able to draw the strike lines on the plane. You can see them perfectly well in this direction. You can see there'd be strike lines. It's planar. Okay, let's talk about mapping in predictor feature space. Let me see, by show of hands, does anybody who here is a geoscientist? I'm putting up the participant window so I can see. And by the way, 120 participants today. Epic, awesome, thank you for joining. Show of hands, 20 so far, 21, 30, okay, we maxed out around 40, okay? 40 geoscientists here today. Wonderful. Welcome very much. Very cool. The reason I show mapping in predictor feature space because it's a machine learning methodology that should be familiar to any geoscientist, the idea of mapping. Okay, let's look at that. I got predictor feature 1, predictor feature 2. I'm going to keep it simple, only 2 predictor features. Okay, so 2 inputs from my model, and then I got 1 output, the response. Now I've got all of my training data. You see those points at those locations. I know the response. I know the 2 predictor features because they're plotted there. I can see exactly where they are. And I want to make a prediction at an unknown location. I hope that all of my geoscience friends would feel at home with this problem. This is a mapping problem, but instead of X and Y, this is in fact in the predictor feature space, okay? And it could be hyperdimensional. It could be like 4th, 5, 6, 7, 8th order. It does, I mean, 8 dimensional. It could be any dimensional space. Cursor dimensionality, I won't talk about that, but it does get more complicated in very high dimensional spaces for sure. This is the same as our common spatial interpolation problem. And the way we're going to propose to do it is by using gather the nearest data and take those data and take an average of that. That's the whole idea of k nearest neighbors. And so we have to identify what are the nearest data to that unknown location at which we want to make an estimate. Now, what's very interesting, I hope you can see immediately, in order to do this, I'm going to have to identify which data are closest, which are the data that I should pool together in order to make that estimate. And so I need to calculate a distance measure. And the distance measure I'm going to use is Euclidean distance. It's really just the square root of the sum of the squares of the differences across all of the different features. Now, what's very interesting is this introduces another important concept, standardization or normalization. If I took my original data set with acoustic impedance and porosity, and I did a distance calculation, can we all see the fact that we would end up with any offset in this direction will seem to be very, very far because we have 2,000 to 6,000 acoustic impedance units. Here we only go from 0.12 to 0.28. So everything seems very close. The whole purpose of standardization is to ensure that we have equal playing field, that all of the features, their changes or their ranges are equally important in the distance calculation. So after we normalize porosity, normalize acoustic impedance, we could draw a line rotated and the distances would all stay the same. It's would be nice and spherical, nicely behaved. Okay, what happens if we don't do that with a nearest neighbor approach? Well, if we use the original features and we translated the porosity to fractional porosity, we would get these crazy striations. The way to think about it, it's like our problem is collapsed to a line. It's like we're trying to make a prediction on a line. If we drew this to scale, we would not even be able to see the model. You see that? And if we go ahead and we use original porosity units, you can still see some striations. If we go ahead and we standardize each, in this case, it's standardization, mean of 0, variance of 1. And you can see we get nice behavior here. The distances are preserved in all directions. We have to do that. Okay, we also get to introduce another concept of k nearest neighbors, and that's the hyperparameter. The hyperparameter is k. That's the size. It really is the number of nearest neighbors to use in the estimate, and it has an indirect impact on the size of a window locally. So what's really cool is because we use k and non-absolute window size, k nearest neighbor is adaptive. In areas of higher density, we don't go as far away. In areas of lower data density, we go further away. If we use a larger k, it results in a smoother response. If we use a smaller k, we get a more detailed model. We can be overfit versus underfit. Okay, this is an example right here. I've been talking way too much and not showing enough code, and I apologize for that. Let's go ahead and get some code ready. Here it is right here. We have a workflow right here. This is exactly what we would have available to you on our learning management system. We have many examples that are ready to go. This is the example for Scikit-Learn. Okay, so let's go ahead. I'm not going to spend time introducing or talking about Jupyter notebooks. That's another topic that we get into, but I'll assume that people have some awareness. It's a workflow well documented with blocks where we can have documentation, equations, enumeration, and then we have code and we can see the outputs. So it's a really nice environment to prototype, to share online and so forth. Okay, let's go ahead and run through this. Now, you'll notice when you work with Scikit-Learn, it's like a smorgasbord. You have to decide which are the tools you want to work with, and you go ahead to Scikit-Learn and you'll import those. Support vector machines, decision trees. I imported some metrics to help us check the quality of our models and so forth. So here's where we decide on what models we want to work with. I built some convenience functions. My convenience functions just simply visualize the model. They just make predictions on a mesh of possible combinations of the predictor features and plot it as a map with the training data so we can visualize. Nice little convenience function right there. We'll go ahead and read in a data set. I'm going to suppress the warnings so that we don't have a bunch of distraction from that. We won't discuss that right now. And I'll go ahead and load my data up. Now you'll notice we can visualize the summary statistics, look at our data. We can go ahead and make some corrections. We have some negative values here. I'm going to truncate them. That's not great data cleaning, but it's kind of a simple demonstration. We can go ahead, if I'm going to build a model, I should pay some attention to the features, their relationships with each other. So I can go ahead like this and calculate correlation matrices. Yeah, when we talk about multivariate analysis, we'll talk about the limitations of correlation. Of course, correlation causation, correlation and outliers. There's all kinds of issues with correlation, but we still look at it to see a potential redundancy, collinearity between our data. Maybe we won't be able to see multicollinearity, but we can see something. Let's go ahead and we'll look at matrix scatter plots. This is on our entire data set. We got production is what we're going to try to predict. And we got vitrinite reflectance, TOC, brittleness, acoustic impedance, log, permeability, and porosity. For the purpose of my demonstrations, we'll select two features, porosity and brittleness, I think, and we'll go ahead and we'll build models like that. Yep, we're going to work with, acoustic impedance, in fact, that's interesting. Okay, so I got acoustic impedance and brittleness are my two predictor features. Now, what's interesting is this workflow is completely flexible. You could go ahead and just substitute whatever you want to work with and just put it in. So you could just change this and you would get a totally different model you could work with, just for experiential learning. In the regular course, I would have you do that and try to build a better model than I did. This won't be the very best model for sure. I didn't pick the very best parameters. Okay, and so we got our test and train data sets, acoustic impedance, brittleness, and production. We got the test data set here, the train data set here. Let's make sure we're doing pretty fair test train. They have similar distributions. We're not extrapolating too much. A better way to look at it though, since the problem is in this dimensionality, the two predictor features, and we're predicting the response, let's go ahead and look at the production over, the production is the color code, MCFPDs. And so we can go ahead and see the results, and you can see that there's a pattern here. Ocular inspection is important when we can. I know in high dimensional problems, very hard to look. Okay, let's apply linear regression. Look at the steps right here. We import the specific model, linear model. We didn't add that at the top. Let's go ahead and instantiate the model. What are the hyperparameters for linear regression? Anyone? Linear regression, what's the hyperparameter? Is it a trick question? What's interesting is that for a linear regression model, I agree. Once you've decided the number of features, the number of predictor features, there really is no hyperparameter. Now, if we got into ridge regression or lasso, now we're talking about regularization terms and so forth, but we're not doing that here. Okay, we're going to fit the data to the fit the model to the training data. We use the fit command right here. Yes, Hisham, you're exactly right. No hyperparameters. It was a trick question. Okay, we can go ahead and we fit. Then we can go ahead and we can take a look at our model. So let's do that. Let's go ahead. We fit the model right here. Just fit one feature and it non-linear. We're in trouble now. We're on very thin ice, as we say in Canada, and this is production right here. What we can do next, now can everyone still hear me? I'm seeing I got a little bit of an internet issue, but it seems like it's gone away. Can you still hear me? Yeah, all right, I'm good. Thanks, Chris, Mohammed, everybody, Sue. Thank you, Todd. I appreciate the feedback. Very helpful to me. Okay, and then we can go ahead and we've done that. We can make predictions at the testing data locations and quantify the error at testing data locations. Okay, for the brittleness model right here, lots of error, linear model's not flexible enough. We know it's gonna have high, wait, what do we call that? When we have lots of error because the model's not flexible enough, what do we call that? Anyone? Yeah, okay, good. I like that. Underfit, model bias, 100%. Model bias. That's because the model's not flexible enough. That's that source of error. And you can see a great illustration. This is high model bias right here, but low model variance. Our model would not be very sensitive to the data. Okay, let's go ahead and do multilinear regression. The reason I'm doing this is because all of our models afterwards will be 2 predictor features, 1 response feature. This is linear regression. I've discretized the color so you can see the lines really nicely. It's a plane. It's a simple plane, right? All right, good. So this was linear regression. Now I also explained k nearest neighbors. So let's cover that too. So here's k nearest neighbors. We go ahead, the first step is we're going to have to do a normalization. I did the normalization by hand. We have methodologies for normalization built right into Scikit-Learn. I didn't bother doing that. I just did it by hand, very simple right here. Then we're going to go ahead and instantiate the model, k nearest neighbors, regressor. Regression means continuous response feature versus classification with a categorical, not a big deal. We got to choose the weights. We can choose the number of data, the k, and we can also choose the measure of distance we're using. 2 will indicate Euclidean, 1 will indicate Manhattan. You can use different measures of distance. We're not going to get into that too much. We can fit our training data right here. Now, there's a deeper concept here. And when you think about it, what's very interesting is that this is a lazy learner. So it really does kind of fit and predict kind of at the same time. So, but I'll just a comment I'll throw in there. Okay. Oh, somebody asked me to zoom in a little bit. Are you having trouble reading the font? Okay. Johannes, thank you very much for that. Or Yar, thank you very much for that. I appreciate it. I hope that's legible to everybody now. Okay, so and then after that, we can go ahead and plot the model. We'll make predictions at the testing data locations. That's all I'm doing here is making predictions for the testing data combinations. Here's the predictions, and I can calculate the score. I don't always recommend R-squared. R-squared really has issues. I would do mean squared error, but here just for simplicity, we did an R-squared. It communicates the idea of variance explained for linear models only, really. Okay, so let's go ahead and plot that up. Take a look at it. We got variance explained 40%. This is our model right here. Here's the training data. Here's the model at all locations. And here's the error in our model. Okay, experts in machine learning, tell me what we can do to improve this model. Let's do some hyperparameter tuning by hand. I had 100 nearest neighbors. What do you suggest I do to maybe improve the level of fit of this model? Anyone? Not doing hyperparameter tuning rigorously, but let's just go ahead and make a change. Reduce the number of neighbors. Okay, what do you think? Anybody want to give me a number? I got 100 right now. 50, okay, I got a 50. That's conservative. 15 neighbors, says Thatcher, and an exclamation mark. Hey, Thatcher, howdy, and Hookham, one of my students from class. Thank you for joining us today. Okay, let's go ahead. 15, because Thatcher put an exclamation mark. That looked pretty enthusiastic. Can you see what happened? The degree of fit of this model has definitely become more flexible. It's better fitting the training data. But look at the variance explained in testing. Look at the distribution right here. If we were to do a robust, rigorous test over many different numbers of data, I bet we'd find out that we're not getting too much better in testing the real world use of the model. This complexity may not be helping us. Okay, I got a please for 30, so we're definitely going to run it. Somebody says please. I do like that better. I do like that a bit better. It does look like a little bit higher variance explained. Okay, powered, I like this. We're getting some interesting ideas right here. Somebody tell me what this model will look like with one nearest neighbor. Anyone? What will it look like? Well, yes, I love it. Like a bunch of polygons, right? Okay, let's see what that's going to look like. Let's go. I love it. People are giving me code snippets. That's epic. Yeah, you can see what's happening with one nearest neighbor. It's just basically giving you precisely the data values at every location. You see that? So it's just going to be 100, it's going to be precise, but look at this. It's terrible in testing locations. You have a worse model. Okay, let's go ahead and let's go back to the lecture slides and let's talk about segmenting predictor feature space. Hey, thank you very much for all of the great comments, guys. I do appreciate all of the interactivity. I do feel a little bad because we just don't have the time to spend in good discussions like we would in the real course. We are just trying to rush through a bit. Another way we can make a prediction is we can segment the prediction region, the prediction feature space into regions. And what we do is then we'll just say, let's make the prediction of the average or the most common category in each one of those regions. Now, what's interesting is we have to come up with a way to segment. A very good way to do that is we can go ahead and build mutually exclusive, exhaustive segmented regions. And when we do that, okay, I'm just going to close my doors really quick. I hope everybody can understand. I've got my family at home, my daughter at home, and everybody here, and it started to get a little bit noisy. I hope you weren't hearing noise. Okay, so what we want to do is we want to find the very best segments such that we get the very best estimates of each one of these exhaustive, mutually exclusive regions. We use just the average of the training data as an estimate. Oh, thank you very much. I appreciate that. Thank you very much. Put in presentation mode. I appreciate that. Okay, so how do we construct the regions? Now, as a geoscientist, I would want to draw it in. I would want to do this. But if we do this, look at the complexity. It would be a HYPERPARAMETRIC setting. It would be a complicated model indeed. Can I convince you to accept that? Are you willing to accept that? Okay, let's go back. That versus that. And if you look carefully, the color coding is low production is bright red, dark colors are high production. There is clearly a trend right here. If you can accept this segmentation, my friends, then you are dealing with a simple binary hierarchical segmenter. And that, my friends, is a decision tree. It's so easy. It's so easy to build. They're very easy to visualize. They're easy to understand. Okay, so let's go ahead and look at decision trees. Let's build a very simple decision tree. I agree. You know, it's interesting if you look at, Andre, if you look at the decision tree segmentation, you might think that maybe there should be a segment here, a segment there, and so forth, some type of interpretation on top of it. I really do appreciate the fact that we can visualize these models in low dimensionality and make those types of interpretations. Okay, let's go ahead and build the decision tree. Okay, how's the font size? Can you guys see that? Everybody can see that okay? Let's go ahead and do the same thing with a decision tree. Thank you very much for the feedback. I appreciate everybody. We'll go ahead and we'll import tree, Scikit-Learn tree. We're going to instantiate the tree. Now the hyperparameters we work with control the depth of the tree, the complexity, the number of divisions. Let's go ahead and just use one hyperparameter. We'll go ahead and set it as something like the number of nodes that we'll allow in the tree, like 6. This should be an underfit tree. Then we go ahead and fit to the data. We can visualize the model. We'll make predictions at the testing location. We're experts at this, and we'll look at the R-squared again just for a quantification. We set a maximum of 6 nodes, which really would be like on the order of a branch. If we have one branch, we'll get 2 regions or nodes. If we put another set of branches, we'll get 4, and then we just put a couple more, we can end up with 6 separate regions on our decision tree. This is the error we describe, 0.39 of the variance, once again with the limitations of R-squared. Okay, what would we do to get a more complicated decision tree? Okay, somebody give me a number of regions or nodes to overfit this. Anyone? 42? Where did that number come from? Is that the answer to everything? Okay, 42, I love that. Thank you very much, Rebecca. That was actually really funny. I do appreciate that. Okay, there you go, 42. We're now got 40% variance explained. This is starting to become similar performance to what we saw. We can see overall the distribution of error, and we could do a proper cross-validation, and we could get the right level of complexity for our model to optimize performance in testing. But, you know, because I used to be a fan of Mythbusters, I like to break things. So let's go ahead and set it as a very large number and see what we get back. You can see now, would you agree with me that we're now fitting data noise? Would you agree that this model is just becoming kind of noisy now? I would agree too. And look at our performance in testing. We are reaching that point where the testing error is going up, the training error is going down. We are overfitting our model. I don't like leaving a model like that. It's kind of almost upsetting. Let's go ahead and put something more reasonable in, like that. We have a very good performance now, and let's leave it like that. Okay, let's do one more modeling method. Mythbusters is awesome. And I heard they're coming back, right? Did you guys all hear that? Jamie and, oh man, those guys are awesome. Yeah, okay. Let's go ahead and let's talk about one more methodology, okay? This is projecting to higher dimensional space. Now, we could have covered artificial neural nets, random forest, gradient boosting with trees and so forth. Decided just to pick something kind of a little more obscure, complicated, because it's very interesting. Okay, so a powerful supervised training methodology. This is a powerful predictive model. And what it is, it's the whole idea of how do we come up with the best segmentation boundary, the boundary in the predictor feature space, so that we can do classification. Now, if it was a spatial problem, your boundary would look like this, and people do that with regions in the subsurface when they do geomodeling. For multivariate boundaries, it would look something like this, and we may want a complicated or a less flexible boundary. We have to make a choice. Now, the support vector machine is a generalization of a linear decision boundary for classification. You can also do prediction with it. Applied for classification with optimal separating of separating hyperplanes when the classes overlap. The whole idea is to come up with a great method that works when the two categories are noisy and on top of each other, and it does a nice job with that. Nonlinearity is actually achieved by projecting the features to a higher dimensional space. Now, in the simplest manifestation, that would be like a basal type of expansion, like they do with polynomial approaches and polynomial fitting, but it can be much more complicated than that. In fact, there's some really crazy stuff where you can actually use the kernel trick to work in infinite dimensional space and still get a model. I'm not even going to talk about that right now, but it's crazy. You can actually, because with the kernel trick, you never have to go to the space, which is really crazy. Okay, maximizes the margin, the separation between the classes, which is important. You want good separation. It only uses the training data that are close to the boundary, within or on the margin, which is really, really interesting. Okay, so you're going to form a boundary with the largest possible margin between the different classes or categories as shown here. Data within the margin or misclassified, in other words, data right here, or if I had a white point on the other side, those are considered to be support vectors and they impact the model. Okay, the C parameter controls the penalty of misclassification. The inverse of C is a regularization. Okay, so we get a more specific model versus less specific model. Our hyperparameter is C. Okay, I'm having too much fun. I'm gonna run out of time. Let's build a support vector machine really quickly. Support vector machine instantiates support vector machine. The kernel we're going to use to project into high dimensional space, a radial basis function, not a big deal. We'll use the C of 1, and we have to do some iterations now with this methodology to get it solved. I hope that's enough iterations. We'll visualize the model. Let's go ahead and just run this. Okay. This one will take a little bit longer. I think another couple of seconds and we'll be done. There it is. What happened? How's that model? Do you like that? Is it underfit or overfit? Anyone? If I increase the C, exactly underfit. I dampen the regularization. In other words, I can increase the flexibility of the model. Okay, so that's what I did. Okay, so by doing that, we kind of narrow up that margin, in fact, and we end up with being more sensitive locally. Is that getting better? Are you guys happy with that yet? I don't like it that much either. I think that's not sensitive enough. Let's boost the cost coefficient here. More, Johnny calls for more, we're giving it more. Yes, 2 orders of magnitude. Is that enough, Johnny? You good with that? Yes, you can optimize. In fact, with all of the hyperparameters we're showing, we could have done a proper cross-validation, k-fold validation. We could have actually tuned the hyperparameters carefully. For this quick 1 hour, we're just doing by hand walkthrough, just showing the idea of the machines, making them and doing it by hand. Not a bad if we're comfortable with R squared, we should be looking at mean squared error, really. Okay, so I want to finish up right there. Let's go ahead and just finish up. I should ask Avi or Kunal, did you have something you want to say here at the end, or am I just good to finish up?
Yeah, I'm good, Michael. It's all up to you whenever you want to close.
My speaker turned off because I've been off, hadn't heard anything for a bit. Okay, Avi, can I hear you now?
Yes, it's all up to you, Michael, whenever you want to close.
Okay. Do you guys want to hang out for just 3 more minutes? Can I ask you some questions to see if, I want to see what you guys learned. Are you guys cool with that? Anybody who needs to bail, cool, I get it. I shouldn't run over time. Okay, so let's go ahead. I want to ask a couple of questions about machine learning and see what we learned here today. Okay. Can you guys see this poll question right here?
Yes, Michael, we can see it.
Awesome. Thank you, Avi. I appreciate that. And thank you very much, everybody else, Evan and others who jumped in. Machine learning. Select the aspects of machine learning. Remember the definition from Wikipedia. A toolkit of algorithms, train with data, improve their performance through training without being explicitly programmed for that problem generalization. Or is it all of the above? Is machine learning all of those? Okay, I've got, hey, thanks for the high level participation. We're at 50 responses already. I'm going to shut down the poll in 3, 2, 1, and I'll share the results. Okay, you guys nailed it. You nailed it. You know, no one would get a 0 on this. All of those are aspects, important aspects of machine learning, but all of the above. That's what machine learning is. And that's why I can't disprove linear regression. Go ahead, look at all those elements there. It really does, to me, linear regression does all of that. Okay, let's go ahead. I'm going to ask, just if you don't mind, 2 more questions. Okay, let's see if, I want to see if you retain this. This is important. Machine learning. K nearest neighbor has a hyperparameter K. How does a too large K impact the model? Does it result in underfit, too low flexibility, or overfit, too high flexibility? Which is it? You know, this is interesting. We're at 40 solutions and 40 answers, and we're pretty split. We're pretty split. Oh, yeah. Yeah, and there's a question about the difference between K nearest neighbor and random forest. Oh my gosh. If I was to compare random forest, I would think more about decision tree with an ensemble approach and bootstrap for bagging. That would be a great conversation to have indeed. Okay, let me go ahead and end the polling and share the results. Okay, let's see. What do you guys think? A larger K causes you to use more data. If you set K to the total number of data, you would estimate with the average of the data at all locations, the ultimate underfit. If you use too large of a K, you're going to in fact be underfit. I know, don't worry about this. I find it confusing too. It often is counterintuitive when it comes to K in nearest neighbors. Okay, great one, guys. Thank you. Okay, let me go. I'm going to do just a couple more if you don't mind. Okay.
I'm going to add a quick plug in here, Michael, while you're pulling up the next one. If any of you want to, Michael does some great topics on the differences with K nearest neighbors, decision trees, a whole lot of machine learning methodologies in the longer courses as well. So if you want to join us for the longer ones, please feel free to check those out.
Hey, thanks, Avi, for advertising that. Okay, so machine learning. Decision tree segment the predictor feature space to make a prediction. What is the prediction? How does it calculate the prediction for a decision tree? Is it the average of all of the estimates from each decision tree? Is it the average of the training data within a region for the prediction case? Or is it the average of the testing data for within a region for that prediction case? Okay, I've got 20 responses so far, all y'all. Thank you very much. All right, this is interesting. This is evolving. I think who changed their answer? I think somebody had a second thought there. I'm seeing some answers change. 60 responses. I'll close it in 3, 2, 1. All right, let's see what we got. Share the results. Nailed it. Nailed it. Remember, guys, it's the average of all of the training data within that specific region that the testing case or the real world case lies in. That's how you make the prediction. It's just the average of all of those. Now, I did get a little tricky because I'm a prof and I got to kind of like fool people a little bit. It's not the average of the testing data. The model is formed with the training data. That parameter of the average value in that region, those are the parameters for a decision tree, and they must come from just the training data. Remember, I said no peeking. You don't get to peek at the testing data, okay? All right, let's go ahead and I'll just find maybe one more. Oh, support vector machine question. Got to do that. It's kind of trippy. I wish we had more time to talk about that projection to high dimensional space. Support vector machine project the predictor feature space to a higher dimensional space. In the higher dimensional space, what is the decision boundary? What is the equation? Is it polynomial? Is it empirical? It's just fit with no functional form, fit to the data? Or is it a linear boundary in the high dimensional space? What do you think? I see 30 responses so far. Thanks a lot, guys, for hanging out. I do apologize for running 6 minutes over, but it's kind of fun, isn't it? Okay, I got 60 responses now. I'll end in 3, 2, 1, and I'll share the response. You know, sometimes professors do a good job making really tricky multiple choice questions so that they can catch almost everyone. This is one of those cases. And so, and it also might be the amount of time we spent on it. But in general, this is the fascinating point. I want to make this point very strongly. In the projected high dimensional space, the model is linear. And I showed an image in the notes where it was like a linear model, but in the low dimensional space, when you project back, it becomes non-linear. Isn't that cool? It's so cool. You can use a linear model in a high dimensional space and it becomes non-linear in the regular space. Fantastic. Okay, guys, really good. Thank you very much to everybody. This has been a pleasure. If anybody has feedback or comments, I'll hang out here if anybody has anything they'd like to add about improving it. I'm from industry, so we do plus and deltas. So if anybody wants to provide something on the chat window, I do welcome that. Thank you very much for your feedback. I do appreciate that. Hey, you bet. My pleasure, Sue. Thank you for attending today. And Turan and everybody, yes. Awesome, Johannes. Hey, I appreciate you guys being very interactive. I saw a lot of great comments from all y'all. I do appreciate that. Sorry I could not respond to every one of them, in fact, which is a great thing, isn't it, to have a short course discussion where there's so many people interacting. I'm a professor. I'm super easy to contact. I can't hide. If you Google search me, you'll find the department website. You'll find my contacts. You know, professors are, you know, you never can go into a witness protection program. You're so visible. Okay, and Rebecca, thank you very much for calling it fun. Fantastic. Made my day. Thank you. I do appreciate that. Epic. Awesome, guys. Thank you. All right, Francis, thank you for joining from a far away. Thank you for coming in. Hesham, thank you for all your feedback. I saw you, if we were attending in purpose, my sense is you'd be one of those experts with the really tough questions all the way through, and I do appreciate that in the classes. It makes a great discussion. So thank you for contributing your experience. Avi, there's some questions here with regard to recordings and so forth. Are you watching that?
Yes, I just saw that. I was just going to say it. So yes, this lecture will be recorded. I'm going to be editing and snipping a bit, and then we'll be uploading it to YouTube, and I'll be sending it out. But be sure to subscribe to our social media and stuff as well if you want to stay in touch with other recordings. So to answer the question, yes, it is recorded.
All right, I'll be back in just 1 second. Sorry, I ran away. So I'm looking up front and someone started cutting the trees in my front yard. Oh, can you still hear me?
Yes, Michael, we can hear you.
Okay. Yeah, somebody was on, I have a big front window here and somebody was cutting my trees in my front yard.
Is that related to the internet thing or?
I don't know. And so what's funny is I had not ordered someone to cut my trees. So I just wanted to make sure before they did too much cutting.
Yeah.
That there wasn't, my trees weren't being accidentally cut. No, it turns out it was the community and they were worried about the trees being too low over the sidewalk or the road.
Makes sense.
So that's fine. So yeah. Okay, good. Any questions, any comments from anyone? Okay. Hey, thank you, Mohammed. I do appreciate that comment. And thank you, Angel. I appreciate it. Are we friends on Twitter? All right. Yeah. Okay. I know you. I've seen you on Twitter. Hey, howdy. Thank you for joining in. Appreciate it. So, Avi, may I ask, what did we peak at? How many people participated today?
We got up to 120 attendees.
That's pretty good for a webinar, isn't that?
Yeah, everybody stayed throughout the whole time, so it's good.
Okay, and I see Johannes. Sorry, you subscribe Geostats guy lectures on YouTube then, or is it also GitHub? Yeah. Okay. Cool. You know what's funny is my twin brother in Canada contacted me. And he told me his best friend in Leduc, Alberta, is watching my YouTube videos. Isn't that crazy?
That's so funny.
That's really, really cool. And he's a person who's just interested in learning about new tech and so forth. And so I just thought that was wonderful, like so cool.
Not even in the industry then.
Yeah, yeah, exactly. Works in a very different industry. That's for sure. Yeah, we'll have the same format for the webinars as we go, right, Avi? Are we gonna mix something up?
No, correct. Yeah, we did a summer webinar series, which was 3, and that had a good one. And this is the first of 3 for the fall webinar series. So we'll have a couple coming up. If you want to see all of our events, it's datum.io/events. So feel free to join us on any of those that are listed.
Awesome.
You have some fellow Canadians in the crowd as well, Michael.
Wait, Hesham misses Alberta. Oh my gosh, can we need to unmute him. There's a conversation we need to have.
Let me get him. I knew you'd be too excited about that one.
Yeah, I'm sorry. As soon as that happened.
Hisham is unmuted here.
Are you from Alberta?
Hello.
Hey,
this
howdy.
is Hisham. Howdy, sir. How are you doing?
Good.
I'm originally Palestinian, but yeah, I spent many years. I studied, worked in Calgary and different places. Yeah.
Now, so with University of Calgary.
Yes, sir. Cruz.
Cool.
Yes, Cruz Research Group.
Very cool. They have a great geosciences department, don't they?
Yes, they do. They do. Yeah. Yes.
Very cool. So I did University of Alberta the whole way through.
Wonderful. Wonderful.
And I grew up just south of Edmonton and Leduc, small town there.
That's why you guys very solid math and yeah, I always admired UFA. It's excellent school actually.
You know, it's interesting. University of Alberta, when I was there, was the largest engineering faculty in the whole country.
Oh.
And there were lots of areas, like in my area, geostatistics, we had Clayton Deutsch there. It's fantastic, like just a great program, world class. So, you know, yeah, University of Alberta has been great.
Awesome, awesome.
Greeting from Oslo too, I see. Hey, howdy. Now I have to ask you, do you get back up to Alberta?
Yes, my house actually is in Ottawa. I didn't buy a house in Calgary, but definitely every year I go and, you know, I always miss Kananaskis and all these very nice places.
Well, I'll tell you what, Ottawa and that down east is just a beautiful part of the country.
Yes.
Amazing, right? Just wonderful. Oh man, you're gonna start getting me a little bit sad. I'm gonna start missing those seasons, you know? Yeah. You'll be happy to know, for Canadians out there, I do drive a Jeep with no doors, no roof, and I never put the doors nor the roof on, no matter how cold it gets here. Because
cool.
It's like what's the worst it gets here in Austin or in Houston? Like what, like 5 degrees C?
Yeah, but hurricane season is always horrible.
Oh yeah, yeah. Well, then I have to put a little bit of a top on so I don't get wet. And from Bolivia too. Awesome. Very cool. I love this whole like, put a webinar out and everyone can join in. It's just fantastic. Thank you for joining.
South Africa as well. We had quite a
few. We have people from South Africa too.
Very cool.
Fantastic. I really enjoyed, I had a chance to visit the Karoo Basin. Look at the rocks there. All right, Glenn, thank you very much for joining. Appreciate it.
Yeah, I think this is the most international webinar we've had, Michael.
I don't know what it is. Like, I think, what do you guys think? Can anyone tell us how it is? I think it's Twitter. I think being able to advertise on Twitter and just engage with a broad audience. You know, we got people from Iraq, we got people from Nigeria. This is fantastic. We should have a map with like little pins.
Yeah. Where we've had students from. Yeah, where you've had students from. Yeah.
I bet you anything, we would have a very complete map by now.
Quite a few pins, yeah.
Yeah, yeah. That'd be epic. Also from Iraq, hey, Gabriel, thank you very much.
Yeah, Michael, I think quite a few machine learning groups picked up your tweet and retweeted it and reposted stuff. So
okay. Well, I had an epic Twitter week where that one went viral. Like it was crazy. It just kept going. You know, Ecuador. Thank you very much, Angel.
Very impressive.
Nova Scotia, the Maritimes. Jeez, it's so bad. Every once in a while I get a Canadian student in my class, and I had one Canadian student in my class, and next thing I knew there was beer in my Jeep. It was so funny, like Molson Canadian 6-pack in my Jeep. They don't worry, grad student, they were of the age to purchase beer. Don't worry. Yeah. But they threw it in the Jeep. Hey, well, thank you very much for that. Appreciate it, Hesham.
Michael, I think actually your next webinar is going to be decision trees. So I know that person was asking about decision trees as well. So
do we cover a little bit of random forest, or is it just decision trees? Can we put a little random forest in?
Yeah. I put ensemble trees, and so whatever topics you want to. Yep. I know we only have an hour on these, which always condenses a lot of the material. But
Yep, I agree. I agree. Let's do that.
Yeah, you even got to the workflow today too, which is awesome. So. Michael, I might close up this this discussion here if that's okay with you. I know you're busy today.
It's just too much fun. I almost feel like we should throw mute off for everyone and just have like a hangout here.
With them all around the world. So.
Okay.
Great discussion today, Michael.
Hey, thank you very much, Hesham. Thank you very much. And everybody, thank you. Avi, thank you for all your hard work behind the scenes to keep this running. Super appreciate it. Thank you.
Stress. Thank you, Michael.
All right. Everyone stay safe, okay?
You too.
Okay. Bye-bye. Bye.